Hello everyone. This video is going to go over something called the ambiguous case of the sine law. So, what is the ambiguous case? Well, we have to lead up to it by looking at a few other things first. But basically, when you're looking for an angle using the sine law, you can actually have up to 3 different cases. You could have a triangle that doesn't exist, a triangle that's actually a right angle triangle, or the ambiguous case, which would be 2 possible triangles to the solution to the question you're looking for. So how could that be? Well, let's start at the beginning here. I have an example given to you where I'm telling you that angle A is equal to 40 degrees, side A is 15 meters, and side C is 10 meters. So the question I'm asking is there any way that this triangle couldn't exist? And that question is going to make a little bit more sense with the actual second example I'm going to show you, okay? But let's just talk about this example here. So here's the given information drawn out, and I actually drew it out with a protractor so that I could get it as accurate as possible. I did not draw in the side A. Now I want you to notice that side A is opposite the 40-degree angle. And I've been talking about the key to the sine law being a given angle and its opposite side given as a number as well. So little a is the key side, okay? Now that's going to be important. So, and I'll explain why in a few minutes. Let's say I asked you to draw this triangle. Is there any way that this given information wouldn't actually form a full complete triangle, whereas for instance the 15-meter side here wouldn't actually reach the opposite side? And the reason that that's a question to even be asked is because this side length here, we can make any length we want. Okay, we're not limited in any way because they didn't tell us what that length is. We do know it has to meet up at a 40-degree angle here, so it has to stay horizontal in the way that I drew it, but its length can be any length, okay? If I drew a 15-meter side length here, now could I draw it just that long? And the answer is no, because this side length is 10. So this length actually has to be longer than 10, right? So, sorry, if I drew it way over here, well, clearly that's longer than 10, but I have to also make it match or reach the base length of AC. So is there a way that it wouldn't reach AC, or it couldn't reach AC? I'm free to make this angle whatever I want. Will a side length of 15 eventually reach side length AC? And it has to. Because it's longer than 10, there's no way that I could not complete that triangle and not have this length reach AC. So I want you to notice here that because the key length, which is 15, is longer than the other given side, a triangle is possible. Okay, there'd be no way that I could draw this that would not give me a triangle. Okay. Now, what if I had this scenario? So triangle DEF is defined as an angle of 40 degrees again. D is equal to 5 meters and F is equal to 10 meters. Is there any way that this triangle couldn't exist? So I'm going to put myself into the position of a student here that would be wanting to draw this out. Okay. So let's say we say that D goes here, E goes here, and F goes here. Okay, so I'm going to draw my angle of 40 degrees, right? I'm going to say that little d is the side that's opposite big D, so that has to be 5. So, oh, okay, I got to make it a little shorter. So I'm going to stop there. I'm going to move my f in, actually, just so that it matches. And we're going to say that d is equal to 5. Little f is equal to 10. Here's my 40-degree angle. And we're all good to go. Okay? So this would be like drawn not to scale. And it looks like it works. But it doesn't. So let me prove that it doesn't. If you look at this picture, which I did draw to scale, now we're still free to take this side length and make it as long as or as short as we need it to be. Okay? But here's the problem. Because my key length is shorter than the other length given, I can't do this because it has to be shorter. Okay? That means that if I drew it at this angle, there'd be no triangle that exists. Okay? And no matter where I put it, there'd be no triangle that exists. Now, I do have to be careful, and this is like a little bit of foreshadowing here. Would there be a way to exist if I drew it straight down like that? If this length was exactly half of 10, I could make it work. And remember, we're able to make this length as long as or as short as we want it to. So that would work. Okay? But that would actually form a right angle triangle and not a sine law scenario, because usually sine law you have acute angles, or maybe one obtuse angle. You don't have 90-degree angles for the sine law. But this would all of a sudden turn into a 90-degree angle triangle. Now, why would this length be one that we could consider? Because the perpendicular length is the shortest length between corner E and the length DF. Okay? But otherwise, it is possible that I have no solution to this triangle because the key length is shorter than the other length given. Okay? So, because, that's not how you spell because the key length is shorter than the other length, we may not have a triangle. Okay? Now, when I say the key length, I mean an angle and its opposite side. We had talked about the angle and the opposite side given to you being the key in the sine law. That's what I mean by the key length. Okay? So, and I wrote that down here again. If the key side is smaller than the other given side, when looking for an angle in a sine law question, there can actually be 3 different scenarios. Now, let's look at the mathematics of why there'd be 3 possible scenarios. Okay, just looking at the math of the equation. So this would be the formula that we would use if we were looking for the angle in a right angle triangle. Okay, sorry, an angle in a sine law triangle, my mistake. It would be sine A over A equals sine B over B. The little a here would move over to this side, and this is how we would try to isolate for big A. Okay, we'd be looking for the angle big A. Now, I have to make a little side note here. What is the issue with sine A when we're looking for angles? Well, let's just look at the pure math here. If sine A was equal to a number like 0.4937, we would arc sine that to try to find the answer, right? Now the arc sine of 0.4937 would give us 29.6. So we would have a solution. Now what about this scenario? If I had sine A is equal to 1.53, if I try to arc sine that, I get an error. Why do I get an error there? And what's interesting is if you do the arc sine of the arc cos of 1.3, you also get an error. And if you do the arc tan of 1.53, that one actually works. So I'm doing a little bit of side note here. I'm bringing in cos and tan because I want to make a point. Why does sine and cosine give you an error if your number is greater than 1, but tan, the arc tan of 1.53 actually works? And the reason is because of how sine, cos, and tan are defined. When you're arc sining a value, you're arc sining the ratio opposite divided by hypotenuse. When you arc cos a value, you're arc cosing a value that's based on the adjacent divided by the hypotenuse. And both of those have something in common that the tangents ratio doesn't have. Tangents ratio is opposite over adjacent. What does sine and cos have that tangent doesn't? That is a division by the hypotenuse. And the hypotenuse is the biggest side. So if you divide a number by something that's bigger than it, like 1 divided by 5, you're always going to get a number that's between 0 and 1. A decimal between 0 and 1, like 0.4937 was, right? If you actually have a number like this inside of an arc cos, you're basically saying that the hypotenuse was shorter than the adjacent side. That doesn't make any sense, okay? So we have to have numbers that are going to give us a ratio that's between 0 and 1 when we're using sine and cos and tan. Well, for us, because we're doing the arc sine here, this ratio has to be less than 1. So between 0 and 1 for this to work. Well, if B is smaller than A, if I go back to this picture here, if B is smaller than A, I just told you that there are different possibilities. We could have a scenario where we have a right angle triangle, we could have a scenario where we have no triangle, and then there's one other scenario, okay, which I'm going to talk about in a second. So let's look at those different scenarios, okay? So we're going to have 3 cases here. Let's just focus on case 1 for now. If we mathematically look at this, what would happen if the key side is shorter than the other given side? So the key in this case is B, all right? So if B is smaller than A, one of the possibilities is that A sine B is equal to B. If the top of your fraction equals the bottom of your fraction, what would you get? You would get sine A is equal to 1. Because if the top number is the same as the bottom number, you could have something like 2 over 2, okay? 2 over 2 is 1. What value do you get when you arc sine 1? You get 90 degrees. So this would actually be a right angle triangle. Okay? What about case 2? Well, in case 2, what happens if the top of the fraction is greater than the bottom of the fraction? Well, then you'd end up with a scenario like I was just talking about, where you'd end up with a number greater than 1 that you have to now try to arc sine. Oh, let me use a different color for that one. So if you arc sine 2.73, you're going to get an error. And that actually means that there's no triangle possible. Now, what's nice about those two cases is that even if a student doesn't even think of ambiguous case scenarios, if you start doing case 1, you're going to end up with a 90-degree angle, and that's going to just show you, oh, okay, it's a right angle triangle. If a student doesn't consider case 2 and that happens, they're going to end up with an error. And obviously, if you end up with an error on your calculator, you're going to stop and say, okay, what did I do wrong? I hope at that point that student would understand and have seen the ambiguous case possibilities. Well, this is not actually an ambiguous case here, sorry, but one of the cases that leads up to the ambiguous case, and would realize, oh, okay, either the triangle doesn't exist at all, or they made a mistake somewhere, okay? So you'd want to recheck your math and make sure everything's okay. You'd actually want to go check to see if B is smaller than A. So if your key side is smaller than your other given side, it might be enough proof that if you're getting an error to say, okay, this triangle doesn't actually exist. Now, the actual ambiguous case is the third case. Now remember, this is if the key side is smaller than the given side. If the key side is greater than the given side, we saw that example right at the beginning, we just solve it and there's only one solution. But if the key side is smaller than the other given side, you're going to have case 3, potentially, where you can sometimes have the top of the fraction is smaller than the bottom of the fraction. And if the top of the fraction is smaller than the bottom of the fraction, this is going to look like, oh, it's just one triangle. Because I can arc sine this. If I arc sine 0.32, I actually get an answer. I'm going to do this on my calculator off to the side here. So 0.32. So that gives about 19 degrees. Okay? But here's the problem. Because the key side was smaller than the other given side, that's not the only solution. And the reason it's not the only solution is because of what we were recently discussing with the magic circle. 19 degrees, and I'm exaggerating here the size a little bit just to be able to draw it properly or nicely, okay? 19 degrees is the angle measured from the x-axis this way. That would give us our answer, okay? But there's another one that gives us a ratio of 0.32. The mirror image of that angle, which would be 180 minus 19, which is 161, right? So there's actually 2 separate answers to this question. Which means 2 different triangles could solve this question. And that particular case is what we call the ambiguous case. If you have a key value smaller than the other given side, and it looks like it's solvable, you actually have to consider 2 completely separate triangles with 2 different angles as the A angle to the solution to that question. So let's look at some examples. Okay, so if I ask you to solve this triangle, all right, so solving means find all the unknowns, right? Now, whenever I'm drawing these triangles, it helps me to always put the given angle in the bottom corner. I know a lot of students like to put the given angle at the top of the triangle, but for the ambiguous case, it just helps me to visualize things if I put the A, and you'll see why in a minute or two. So I'm going to do A, B, and C. Okay, so I'm going to draw this line down here, this line up here. This is going to be my 57-degree angle. Okay, now I'm going to put a dotted line where the 15 is for now, because I want you to notice that that 15 is smaller than the other side length that's given to me. Okay, Now I know this is a sine law scenario because of my key, but my key side, 15, is smaller than the other side. So as soon as you see that, you have to say, uh-oh, what's going on? Okay? So what would be the next step? Well, the next step is really just putting it into the formula. So it would be sine so we would be looking for angle C in this case, right? So it would be sine C over C is equal to sine A over A, which is our key, right? And then we would isolate for big C. So we would have sine of big C equals, and now we could start putting our numbers in. So little c is going to go up here and multiply the sine A. So little c is 20. So 20 times sine of 57 divided by little a, which is 15. And this is what we've got to check, right? What is the answer to that going to be? Is it going to be equal to 1? Is it going to be between 0 and 1? Or is it going to be greater than 1? Those are your three possibilities, right? So if, well, let's calculate it and see what it gives. So 20 sine 57 over 15, I'm going to do that. Let me bring up the calculator here so you can see it this time. So 20, actually let me clear everything out here so that you don't get messed up with what's already there. Clear, okay. So 20 times, now this calculator I have to do 57, then hit the sine button, and then I'm going to divide that by 15. Oh, we're getting a number greater than 1. Right? It's giving us 1.12 approximately. So let me transition back to the smartboard here. So that'll give 1.12 approximately, and that is greater than 1. So no triangle possible. Because as soon as you arc sine that, you will get an error. And I find that's the easiest way to check. Just try to solve it as normal, see what happens. Okay? So that's a case where you wouldn't have a triangle. Now, if you had a 1 appear here, all you would say is, okay, it's a 90-degree angle triangle, and you would continue solving it as if it was a 90-degree angle triangle. So those two cases shouldn't worry you, because they'll self-fix. Okay? That you'll notice them right away. It's this example here that's going to cause you a little bit of difficulty, and it causes me difficulty still as well. Okay, so let's draw out this picture. So it's triangle ABC. So again, I like to put the given angle in the bottom corner here. That's a 29-degree angle, so it's a little bit smaller than it was before. All right, so 29.3 degrees. We've got our A side, which is 12.8. And you know what? I'm going to make that as a dotted line, because I want to make sure that it may or may not exist. Okay, we have to check that. And I mean, I previewed this in my head here. I could see that the other given side length was going to be bigger than the key length. Okay, so I looked at angle A and I looked at side A, and then I compared that number to this number, and I said, okay, the key side is going to be smaller than the given side, so key side 12.8 is smaller than the other side. So as soon as you see that, it's an uh-oh situation. Okay? So let's plug it in to find now which angle would we be looking for here. We'd be looking for angle B, right? So angle B, if I set it up, would be set up like this. My key always is the fraction on this side, right? So then we would do sine B, and let's start putting the numbers in as we isolate. So little b is going to come up here and multiply sine A. So it's going to be 20.5 sine big A, which is 29.3, all divided by A side, which is 12.8. So we're going to have sine B equal to, and again I'll bring up my calculator so you can see me calculating this. We've got 20.5. Let me clear everything out here. So 20.5 times 29.3 sine divided by, and you can see that it's already going to be giving me 10. So 10 divided by 12.8 is going to give me a number smaller than 1, between 0 and 1. So 0.78, and I'm going to use 4 decimal places. So 0.7838. Okay, so when I arc sine that, it's going to give me an answer. So I'll do that off to the side here. Sorry, I forgot to switch over to my screen. So I just inputted all of that information. So arc sine of 0.7838. Now I just kept that number, and it's actually rounded to 0.7838. So I kept that entire decimal in my calculator, okay? And I'm just going to arc sine what's on my calculator screen. So that's giving me 51.6. So 52 degrees, approximately. Okay, now here's where the work actually starts. Okay, we now need to go in 2 different directions. If B is equal to 52 degrees, let's solve the triangle. But there's a second scenario, okay? Because of our magic circle, 52 is one of the angles that we have to consider, but we also have to consider 180 minus 52 as well, okay? That'd be 130 minus 2, which is 128 degrees. So, sorry, I forgot to write if B is equal to 52 and if B is equal to 180 minus 52. So we actually have 2 different solutions we now have to consider. All right. So if we look at my original picture here, if B is equal to 52, so we've got 29.3 we've got 29.3 in this corner, 52 in this corner, and then we could we also have a couple of side lengths there. We have 20.5 and 12.8. Okay, so I think I had labeled that A, B, C like this. I'll just double check that. Okay, so we can now find this angle, right? So angle C is equal to 180 minus 29.3 minus 52, which gives approximately 99 degrees. Okay. And now that we have that angle, we'd have to find this side length AB, which is side length little c. Okay, and we would find little c by using our key value. So, and we're not looking for an angle this time, so we don't even have to worry about the ambiguous case. Okay? And if you don't mind, I'm not going to do the rest of the math here because that is not hard to do. All right? So you're just going to input a sine c over sine a, and that'll give you your c length, and I believe that's the last length we needed to find. All right? So that's the first solution to the ambiguous case. Now we'd have to look at the second solution to the ambiguous case. So if I draw this picture, now b is equal to 128, so I'm going to exaggerate that. So we'd have 20.5 down here. We'd have 12.8 here. This would now be 128 degrees. Just going to make sure I'm not making any mistakes there. This one is still 29.3. Right? And we've got A, B, and C. So this would be the second triangle we'd have to solve for the ambiguous case. So we still need to find angle C. So in this case, angle C is equal to 180 minus 29.3 minus 128, which is approximately 22 degrees. Okay. So this would now be 22 degrees in this case. And to find little c, we would then plug in, I'm going to use the same formula, but I'm going to isolate it here. So it's going to be a sine c over sine a. And we would get a completely different answer for our little c length in this case than we did in that one, which again, I'm not going to complete. And that's how you deal with the ambiguous case. So let me just recap here. If you're given a triangle to solve, or even to find an angle for, and your key length, the key is the again in the sine law is an angle with an opposite side given. If the key length is shorter than the other length, you always have a possibility of the ambiguous case. You then just start to solve it as normal. Plug in looking for the angle that you'd be searching for, which would be the angle opposite the other side. Okay. Plug in all your values. If you end up with 1, you know it's a 90-degree angle. If you end up with a number greater than 1, you know that the triangle doesn't exist. But as soon as you end up with a value between 0 and 1, once you've done this calculation, you now have to split off into two possibilities, where the angle is either 52 degrees, it was in this case, or it's equal to 180 minus 52 degrees based on the magic circle. Because there are two angles that give that ratio based on the magic circle. And then you solve it, finding the third angle for both cases, and then finding the third side for both cases. And if you finish off the math here, you will find out that little c is different in both of those cases. And that's how the ambiguous case works. Now, where can this be an issue? And I had talked about this earlier, that I would come back to this. We haven't seen the cosine law yet, but you have seen it last year. It was something you saw or should have seen in grade 10. This triangle would be a cosine law scenario. Okay, now if I asked you to solve this triangle, the first thing you would do is use the cosine law to find one of the angles. So let's say you find this angle here. Okay, now you have a key, right? But here's the problem, and it's not a problem for this one, the way I set it up, because if this side length was smaller than one of the other two side lengths, which it isn't, okay, then you would actually have an ambiguous case scenario. So for instance, what if a student had found this angle instead? This would be your key to finding the other angles for the sine, and usually we use the sine law at that point, okay, which might not be the best solution. But let's say a student had found this as their angle, right, and then they had the key this way. Well, 15 is smaller than 20. So if you went and found this angle next, that would be an ambiguous case scenario. You can't do that. So this is where it will become an issue. And I'm going to talk a little bit more about that when we get into the cosine law, okay, which will be the next lessons. But that's where this can be an issue. So we're going to end the lesson there, folks. And when we get into the cosine law, we'll talk a little bit more about the ambiguous case. In homework today, you're just going to be working on ambiguous case scenarios and checking to see which scenario do you have. Is it is it an actual triangle? Is it a right angle triangle? Or is it an ambiguous case triangle? And working through the solutions for those triangles. Have a great day, folks. We will talk soon.